Okay.
Okay, so now we have a really fascinating talk here by Marc, Blanch from the BBC about their work in autocorrecting black and white to colour.
Okay.
So if we give a round of applause.
Okay, thanks everyone. I'm Marc. I'm a graduate engineer in BBC Research, and I want to present our talk in automatic correlation using GANs. So this work was presented last 2 weeks ago in Malaysia. So it's like the work from my PhD project in the BBC and also in the DCU, Dublin City University. So first of all, just to quickly introduce what is colorization. So colorization is the process to add colors to grayscale or other monochromatic images in order to get some visual appealing results. So the aim is not to get the real results, because we have a input grayscale image. So the thing is to get some results that are realistic and perceptually correct for people. So correlation was introduced, so a bit of history by this Canadian guy, and he worked for the NASA to colorize some monochromatic footages from the Apollo mission, and he got these kind of famous colorized footages. And also he created after this one company called Colourisation Inc., and he applied these technologies to colorize other programs or TV shows, all TV shows. And a more recent example is this Peter Jackson documentary of the First World War, that he applied colorization and other model restoration techniques to get a colorized version of some interviews, and was provided by BBC and for the Imperial War Museum. So both examples use it some semi-automatic correlation method, in which the computer and the method mainly kind of assist a user or some people to get the correlation results, but it needs a lot of intervention of the user and some artistic experience to get some good results. So some examples of these semi-automatic methods are some recent works. For example, this is Realbased Correlation. We have a technology that helps the user to get a colorized version of grayscale images, and mainly the user replaces some scribbles and some references in the image, and then the system learns how to transfer and expand these scribbles to the whole areas of the image. And another example is the use of an exemplar-based correlation, in which we introduce some similar image color version of the grayscale image, and then the system kind of learns how to transfer the style from the colorized image to the grayscale one, and transfer the areas and get the colorized version. So for our work, we are more interested in fully automatic methods, in which we have an end-to-end system in which we input a grayscale image and we get automatically the color version. But those fully automatic methods has some issues loss of precision, because if we don't have any reference and we only have a grayscale image as input, so there's a lot of ambiguity in which colors could be the real ones and some realistic colors. And also we will go later for this desaturated effect that mainly is due to some methods, machine learning methods based on regression. So we'll have a look now. So first of all, the ambiguity and the results. So if we have a big data set of images, we can have some prior information of the colors. So the system, for example, can detect some high frequency areas on the image as vegetation areas, and then infer some green tones, or the sky could be blue. But there's most of the other examples that is super ambiguous, a car or a t-shirt can be whatever color. So most of the times the system, it learns to infer the most the instants that are most common in the database. We have a database of red cars, so we have a new instance of a car, so we'll be super likely to be colorized red, for example. And then we have this desaturated effect. So if we have a look, for example, the distribution of the color channels of ImageNet, for example, we have most of the examples so it's most of the examples are in the middle of the distribution, in which belongs to some brown color. So if we have a machine learning system based on regression, for example, should converge to the mean of the distribution of the examples, and then like the colors should go to some brown results. So like most of our like goal in this project is like to use a machine learning system to train this correlation task, and then get like some distribution which is like close to the reality, which is like this blue one, which is kind of a broad distribution, having like some in these areas some strange colors, like more saturated colors. So yeah, we apply like in that case also GANs, conditional GANs to get the colors, and we are based as baseline of this pix-to-pix model. So we have like a grayscale image. We use a generator to generate fake colors, and then a discriminator to discriminate if this is fake or not, and then like get like most realistic colors as possible. So yeah, so we have like as a bit of background in GANs, so most of you could know like we have like this discriminator and generator. The goal of the discriminator is to save the colors like belongs from the generator with fake colors or real colors, and then like to have like some motivation to the generator to generate as most realistic colors possible in order to fool the discriminator. And we are also based on the pix-to-pix model and adding like a L1 loss in order like to make sure that the generated colors are most close as possible as the ground truth colors. Here we can see, well, yeah, and then like these both generator and discriminator are like trained in an adversarial setting in order like to compete each other and get most realistic colors. And we have like here architecture. We are using a UNet architecture for a generator. So we have like an encoder part which encodes some of the spatial patterns of the input, and we get like some latent space in the middle, and then we have like a decoder part in which we which interprets like the spatial patterns of the input and assign colors. And then like we add the two generated chroma channels to the input, and we discriminate to apply another convolutional network to classify if this is real or fake. So as we can see here, like as normalization step, we are combining batch and instance normalization. So in the pix-to-pix model, it applies batch normalization with the idea to kind of stabilize the training of the GAN. So most of the problems to training a GAN is like there's like super unstable, and most of the cases like it converts to some local area which is called like this model collapse. So we also apply batch normalization in order to stabilize the training, but also we apply also instance normalization, in which instead of learning like some covariance like in a batch of samples, we learn special patterns of one image in order to track like the style information of the image. So we apply batch normalization as the pix-to-pix model in like in all the architecture, but we apply instance normalization like in the part which closer to the style content of the image when the colors are assigned. So as other idea, we also apply spectral normalization. So this was introduced by attention GAN. So that was like demonstrate like helps to stabilize the training. So if we have like a generator and a discriminator which like super difference in complexity, so the generator tends like to collapse to a local minimum, and then like if we combine adversarial loss and a L1 loss, if the adversarial loss it collapses to a local minimum, like all the weights of convergence goes to the L1 loss, and then we have like this desaturated result because like we are doing mainly a regression task. So we can see here, for example, the blue line is the pix-to-pix model, and so if we apply this spectral normalization step, so we can like kind of prevent the model collapse of the adversarial loss, and then like the L1 loss so has less impact in the convergence. And as a final step, we apply multi-discriminator. So if we go from the baseline model, pix-to-pix model, we have like a patch GAN in which like the architecture of the discriminator, based on the architecture of the discriminator, we are discriminating some local areas of the input. But if we have like a multi-discriminator with varying the resolution of the input, so we can like keep the same architecture of the discriminator, and we can discriminate like different sizes of areas of the input. So we combine like all the discriminators, and we apply like the sum of all the discriminators to the loss, adversarial loss. So as here we can see like the generation of colors like while we are training, and like the behavior of both generator and discriminator in order like to get the final results. And here we can see like some visualization of the results. So this is like the pix-to-pix model, which like this is like not all the examples of the database, but like just like the idea of this desaturated result. And just applying, for example, spectral normalization, we get like more colorful results, and then we can see like the application of multi-discriminator and application of instance and batch normalization together. So that was all. Here again. If we want like some more information, we have like a blog post which links to the paper, and we have like have a look at more details. And thanks a lot. Yeah, that was my call.